Saha madam. So today's topics that Dr. Shailesh Chaure is going to cover are hands-on spatial analysis and application of digital elevation model. So I think we can start, sir. Over to you, sir.
Okay, thank you,
Thank
madam.
you. Thank you.
So, good morning to everyone. Sabhi ko namaskar. Actually, the today's session was to be taken by some other expert, particularly this is special analysis hands-on part. But due to some unforeseen circumstances, that expert is not available. So I rushed to this particular part of it. So anyway, not a problem. So I hope that you might have received the data which I have shared with Gokhale madam, and that data you download, and we will be working on that same data. We'll be doing some hands-on exercises on spatial analysis. So yesterday we talked about the various things like clipping, intersection, selection, buffering, union, difference. So I have provided you some small data set, the same one which I use for my PowerPoint presentation. So first we'll do the things on that particular data. And after that, I will demonstrate you some real life example so that you will have a feel that how exactly these things can be applied to solve a real life problem. So I'm not going to give you that data, but later on, if you feel like doing some hands-on at your end using that data, I can provide you, not a problem. But I think as looking to the time schedule, it will not be possible to conduct so many exercises. So we'll just try something hands-on on the simple data, and then we will try to do it. I'll just try to demonstrate a real life problem. Okay. So today I will not be using for this particular slot. I will not use any PowerPoint presentation. Whatever data I'm having, I will open it in Quantum GIS, and then we will perform certain operations. Okay. So just wait for a moment. I'm sharing my screen. You have received this data overlay example. Okay. So you need not to do anything, just download it, unzip it, and keep it with you. I will give you enough time to do the hands-on. So first you see what I'm doing here. So I'm just opening QGIS. I think before proceeding for the special analysis, I think one thing could not be covered, just a small thing. So I will explain that in 5 minutes time, because the data file which you are having, in that you have got one Excel file, and I think so far we have not used that. And you might be wondering that what is there in this file and for what purpose it has been given. So there's a file called ATMs. It is an Excel file. So I'll just click and open this Excel file. You see what is there inside this file. Okay, you see there is an ID, a bank name is there, deposit facility 1100 means 1 means facility is there and 0 means facility is not there. It can be a field like true and false. Okay. Sometimes, many times on ATM, you have got a cash deposit machine. So that facility is there or not. And then there is a latitude and longitude. So this particular data, this is just a hypothetical data. This is not the real data of Indore. Just for the exercise purpose, some random points have been created and some random names of the banks have been given to it. So don't consider that this is a real data. Okay. So suppose some agency collects this kind of data using GPS or Google Earth or something, and a file is provided to you which is having some point data, maybe a location of tube well or petrol pump or a school or college or hospital, or the location of COVID patient, or any other thing. So XY coordinates are there and some attributes are there. So how to take this data in QGIS? So that we'll see. Okay, it will take only 5 minutes. So it is an Excel file. So QGIS cannot read Excel file. So what we'll do, we'll transfer this data into another format that is known as CSV file. CSV stands for comma separated values. It is basically a text file. So text files operations are quite common, and so many software can read and write the data to the Excel to the text files. So we will just export this Excel file into a comma separated value text file. How to do it? Not a complicated process. Many of you might have already using it. So we'll go to files and go to save as, and then of course we have to decide the location. So I will use the same folder, data for workshop, and here I give, say you see the save as type, Excel workbook is there. So I will expand it and I will select CSV comma delimited. So name will be the same, ATMs, and just save it and just exit from here. So now we have got one more file here. It is Microsoft Excel comma separated value. If you closely see it, you'll find that the icon is different here. Okay. So now you might be wondering that still it is an Excel file. No, it is not an Excel file because it has been created using Excel. So the Excel has given assigned a typical icon to this, but this icon is different than the Excel workbook icon. Okay, so suppose I want to open it in some other editor like Notepad or something, we can do it. So I'll just open with say WordPad. Okay, now you see. First, first row is ID, then comma, then bank name, then comma, then deposit facility, comma, latitude, comma, longitude. Like that, the next row is also having the values separated by comma. So it is a text file, and QGIS can read this file. So we can import the data from other sources, maybe a point data, line data, polygon data. The story for the line and polygon data will be slightly different. So we are not going into detail of that, but the simplest thing is that we can we can import the point data. We can of course import polygon and line, but for that some different format will be required. That is known as the WKT format. So that geometry has to be given in a WKT format, well-known text format. You can Google around this particular thing, and if any one of you requires if he's in need of using WKT format for their research or teaching or their day-to-day work or something, then we can separately discuss about it because the time is very less. So I'm not going into detail of that. Okay. So so you can see the icons here on the left panel. There's the icon add delimited text layer. Okay. Earlier we just imported our data using the same functionality, same menu. So now I click on it, a pop-up menu will come, and then I have to choose a file. So I'll just go to this. I have to navigate to the folder where my data is stored. So it is in the data for workshop, and you see it is already displaying the text file that is not showing the Excel file. So just click on this. Now you see all the columns are visible here, and it is a CSV file, and so it does not know that the geometry is there or not. Okay, so WKT format, if it is there, then we'll select WKT, but the format which we are using is not a WKT format, it is a point coordinate. Okay, so once I select point coordinate, say no geometry is there, nothing is coming on the right hand side. The moment I click point coordinates, that it is asking me which field is holding the X value. So X field is longitude and Y field is latitude. If Z is there, elevation is also there, then that can also be specified. But in this data is not having the Z or the elevation information. Z value is not there. So this is it. And once I'm defining the coordinates, I should define the projection also. Because this data is on latitude, longitude, so I will use EPSG 4326. But if you got some data which is on UTM coordinates, easting and northing, so that value will be a huge number. And accordingly, you have to pick up the CRS, that is the coordinate reference system for the geometry. Once you define all this and say add, close it. Now all those points have been added here. It's wonderful. Now, if you right click it and see the attribute table, you've got everything here. Even the latitude, longitude is also visible because that is a part of attribute. So even if you delete this column, these points will not be deleted because it has created extra geometry field out of this data, and it has kept it somewhere in the memory. Now I can export this particular thing by right clicking. I can say export and save feature as, because still it is just a layer in the memory. We have opened the file and just displaying it. It is not a shape file. So now this data we will save it or we will export it as a ESRI shape file. So again, the shape file will go to the same location where I am having all my data. So I will call it ATMs. Need not to give any extension because we are asking it the format we have already chosen. So you need not to give the extension. You will give the name of the file and say save, and because it knows the geometry, so it is not asking that what kind of geometry is there. And CRS is EPSG 4326, which is correct, and say OK. One ATM layer has been added here. Now we have to remove this one because the work related to this particular file is over. Now this is our file and we can do whatever we want with this. Okay. So let us see some special analysis examples from here itself. Okay. So I will not use this file. I am already having this data somewhere on my computer. So just a moment. I think just a minute. Just a minute. I will just locate the files and we'll just let you know. So for the time being, I am just putting off my presentation because I have to explore my computer. So I'm stopping this presentation. And in a few minutes, I'll just locate those files and we'll be sharing my screen again. Okay. So okay, fine. Okay, so I got the files which are required. I'm putting it on my desktop here. Okay. Okay, fine. So this indoor data for map composition, this folder is there. And I hope this will be given to you also. And it has got all the things. This ATMs are there, road and tehsil and places, everything is there, railway track. So whatever the data which you're supposed to create in this training program, the final files for this particular data is already there. So you can use some basic, you can apply some basic spatial analysis on this data. And you can also use this data for map composition, for coming up with a beautiful, properly designed map. Okay, because many of you may not have completed the data creation. That is why purposely we are providing the final data. Final means just a presentable data, because there is always a possibility to enhance the beauty of this particular map or something. So it is endless process. So a fairly good coloring and this thing has been done, but that can always be manipulated and done the way you want, even far better than what you are seeing on this screen. So that is not the issue. So the thing is that we should know how to design it. So I think it has not been very well emphasized during the training, but you can always go to the particular layer, go to the properties, and using this particular dialog box, you can change the symbology of the layer. You can put the labels on the layer. And in symbology, if you explore, you will find so many options. Even the transparency of the layer can be manipulated, can be modified, because there is an option called layer rendering. Here you can just do the various other things for this. Okay, so even if you go for this thing, so you can see the fill color, you can stroke color, stroke width, and style, and so many things you can change here. So this is that opacity. I was talking about the transparency. So I'll just show you how this transparency will work. Suppose I take this layer onto the top. Everything is hidden now. Okay, now take this, right click on it, go to properties, and go to symbology, and select, okay, this will be a problem. Okay, no problem. So there you see the opacity. So opacity is 100%. Now I reduce it to say 36% or something like that, and say apply, and okay. Now you see the layers which are below this particular layer, they are appearing. So this way, in using the various options which are available here, we can come up with a beautiful a map, and can always use it for the presentation purposes. Okay, now I've done it in a reverse way. Anyway, so that is it. So we have got the ATM data with us. I will just add this to this particular map. So ATMs.shp, open, add, and close. Now the ATM points are coming. Remember that these ATMs are not the actual ATMs, just the random data for the exercise. Okay. So I'll just remove other things. Roads I will remove, railway track I will remove. So we have got the Tehsil polygons, and there we have got the ATM points. And I'm interested in extracting the ATMs which are falling inside Indore Tehsil. How to go about it? Here the spatial analysis can help me. How? I can just go to the vector processing tool, and I can say clip. Cookie cutter, you remember that. So you got one point layer. You are putting a that point layer is having so many points, and on that you are putting a polygon. So what is that? Just a minute. What is that point layer? This is that point layer. Okay, I'll remove this also. This is the point layer, and you don't know which point is falling in which polygon. Of course, once you put a Tehsil map, you can see it. But suppose you want a list of it, or you want to process those points, you want to count the number of ATMs, and again you want to perform some kind of other analysis, then what you'll do? You will manually note down them and enter them again and do it. So no, that is not a thing which we do normally in a computerized system. We ask the systems to automatically extract the things for us. So how it will be done? I have to select a polygon which I want to. So for selecting again, say ATMs is selected, current layer, and if I click on this, nothing will be selected. So I have to select the layer from which I want to select some feature. So my current layer is Tehsil now. I go to select feature, and click on this. Now that Indore Tehsil polygon has been selected. Now whatever I will do, whatever analysis or vector processing I will perform, that will be performed on the selected polygon. Okay, so I'll go to vector, geoprocessing, and then I go for clip. And here you see it is asking for input layer. So input is point data which I want to input, and I want to perform some processing. So that is ATMs, and overlay is Tehsil. And again it is asking that selected feature only. If I click on this, then it will just return me the points which are there, which are being clipped by the selected feature. I have only one selected feature, that is in the Tehsil. There may be more than one selected feature also. And if I don't select it, it will clip the things for all the polygons. So I run it and say close. Now it is ATM. Now this is the result clip. It has created a memory layer, and in that you are having the points here. So now all the things related to, I mean, the attribute of this particular point layer, that is being written. So this is the result. Same thing we can do for roads also. Okay, so just see that also. No, not this. This one. Roads. Now let's see. Vector, geoprocessing, clip. Now because the input layer I want the roads, so that I have taken, an overlay layer is the Tehsil layer, and selected features only, and say run, say close. Now see the clipped, and another one is the, now you see, that is it. So this is how we can perform the clipping operation. Okay, so if you see the attribute table of this, you find that only ID is there because the road layer is not having any attribute, only one column. Okay, that is it. So it is returning only one column. Now, if so, I will, okay, I'll just keep this clip layer, no problem. Okay, I remove, okay, I keep it, no problem. So now this, I can perform one more operation, that is the intersection. Say, if I do intersection, and take ATMs as the input layer, and overlay layer is the Tehsil layer, and again I do it with the selected feature only, that same polygon. I say run. You see it has created an intersection memory layer, and I put off the other things. You see again it is returning me the points inside that polygon. The clip also did the same thing. Okay, but if you see the attribute table, you will find that the attribute fields from the intersecting layer or the overlaying layer, they have been added to this. Okay, say for example I apply this operation on entire data, for example, just a minute. Okay, now this is it, and these are our ATMs, and Tehsil is okay. Okay, so I go to vector geoprocessing, and then I perform intersection. So I input layer I take as ATM, overlay is the Tehsil, and I don't select anything here because it is not selected because I have not selected any. So that is why this particular option is disabled. Okay, it means this operation will be performed on all the features of the layer, means all the 4 polygons of Tehsil layer. Does it? Okay. Now here it has been written this particular thing. So it has written the same thing, but what it has done, in front of each point, it has associated the attribute of that polygon which is containing it or which is intersecting with it. That is something wonderful. So now go to this attribute table. So now you know which particular ATM is falling in which particular tehsil. You can sort them out. So all the ATMs of Depalpur tehsil are listed here. All the ATMs of Indore and Mahu and Saver. So this way you can always create data or just attach the attributes of the data and can do this. Okay. So that is it. Then next operation which we are interested is buffering. So let us try that. So I'm just removing all these intersections. Okay, just let us, before proceeding further, do you have any question related to these two operations, clipping and intersection? Okay, I know that I'm a very good teacher. Hmm, okay, so I will remove this intersection and other things. Temporary layers I have removed. This I will remove. Okay, now I have got roads with me, and so okay, I'll remove the tehsil also. Not remove, I've switched it off. And suppose I select any of the road. Okay, so it is not selecting. Why it is not selecting? Because I have not selected any of the layers from this layer panel. So if I want to select the features from the road layer, so I should make the road as an active layer or current layer. And then if I click on something, okay, this is basically that entire thing has been merged and different features have been merged together and a single feature has been created. That's why when you see the attribute table, you see only one row, but we can always break it off and can make the different segments. Okay, so I'll just put the ATM off, and okay, so let us do it on the entire layer, no problem. So I create a buffer on this road network. Say because this data is on WG. Okay, this is the coordinate of this. Okay, right click on this. Okay, even if you keep the cursor here, you can see it is multi-line string EPSG 4326. Okay. Now, if you just try to create a buffer on this, what will happen? I'll tell you. So you go to vector, geoprocessing, and say buffer. So it will input layer is fine, and buffer distance is saying degrees, 10 degrees, because my original layer is in geographic coordinates. So whatever data is there that is existing, the unit is degrees. So imagining a distance in terms of degrees is a difficult. So how to do it? What we can do is we can export this layer, save feature as, and then here we can say roads will transfer its coordinate, its projection, we'll take it to UTM coordinate, and here we can go for UTM zone 43N. You have to read about the UTM zones. So the UTM zone to which this area is belonging, that particular CRS we will select, and then we'll say okay. So it will create another layer because geographically both the same point at the same area, same location, so they will overlap. But the coordinates are different. The projection is different. Coordinates are same. They are belonging. Both the layers are belonging to the same place on the surface of the earth. Okay. But now see its projection has changed. It is the universal transverse Mercator projection, means the coordinates are in terms of meters. So I can define the buffer distance in terms of meters. Now go to vector, geoprocessing, and say buffer. Now you have got roads UTM. Distance 10 meter will be very less. So I make it say 250 meters and say run, close. Now a buffer has been created. How do you see it? I'll just take it below. Now you can see this is the road and 200-meter buffer has been created. Okay, let us define 200 meters. And now I'm interested in finding out how many ATMs are falling within 200 meters from the road. I think all of them are falling. In fact, they are on the road itself. But anyway, if I put certain points like they are here and there at different locations, and if I perform the clipping operation using this particular thing, in that case, it will return only the. Okay, just do one thing. I will add some more points to this ATM layer. Okay, and purposely I will put some of them very close to the thing, some of them inside near to the road, some of them outside. Okay. So now what this is going to do is, okay, let us see. So now you have fairly good idea what I mean to convey. So now we have got a buffer layer. Okay, this I know because I have created this buffer. This is a buffer of road for a distance of 200 meters. And if I want to store it for future use, I can right click on it and can say export and save feature as, and I can give an appropriate name, 250-meter buffer road, like that some name I can give and can use it. And if I just want to keep it as a temporary layer, there's nothing has to be done. I can just use it. So I go to vector, geoprocessing, and clip. So what I will clip now, I will clip the ATM points. Okay, I think before that we have to save the ATM there. So I'll just go to this and save it. Take the editing off. Then go to vector, geoprocessing, clip, and here I selected the ATM as input layer, and overlay is the buffer layer. And then say run and close. Now see what has happened. The points. So the points which are inside the buffer, only those points have been returned. Other points it has not taken. So this way, the buffer analysis can be used to identify the features which are falling within certain polygon or something like that. And if you want to associate the properties of both the layers, then instead of clipping, you can go for the intersection. Graphically, on the map, the result of the clipping and intersection will be the same. Okay, so that is it. So I think I have explained you the buffering, clipping. So it's better you try some hands-on on this. Okay, one more thing we can try. I can just try to create a polygon. Okay, say for example, this is the district polygon. Okay, and how it was created, I demonstrated you. Okay, so okay, I'll just re-demonstrate it. So Tehsil layer is there. If you right-click it, it has got attribute table, and in that there is a field called district. In that Indore is written. Remember here, if you write Indore in capital, in some field in small, in some field in title case, then all the things will be different. Capital Indore is different than small Indore. So when you write the data for some specific purpose, the style of writing should exactly be the same. Be it uppercase or lowercase, that doesn't matter. But the way you're writing in one column, you should write it the same way in all the columns. Otherwise, you will be able to see the data, you will be able to print it, but you will not be able to process using that particular. You will not perform processing based on that particular data. Okay, so that you have to remember. So let us see how the dissolve works. So we'll go to vector, geoprocessing, and select the dissolve option. And I want the input layer as a tehsil layer, and the dissolved field I want is the district, because district field is having the common values. So I have selected it and say close. Now a dissolved, this thing has been returned. If you see the attribute table, you will find the attribute of the first polygon from the data. It has got no meaning, so we can always modify it. Okay, but the result is that it has returned a single polygon by dissolving the internal boundaries of the tehsil polygons using a common property, using a common attribute value. Okay, so this way, this inner polygon has been created. Now, if you want to perform a buffering operation on polygon, say what will happen? So I'm just removing this. I will use another polygon. This is the polygon, and you might be wondering that why this polygon is in white color. So nothing has been done. Right click on it, go to properties, go to symbology, and filling style, fill style. I have said no brush. So you can fill horizontal lines, vertical lines, hatches, and solid. So no brushes there. That's why nothing is being shown here. So let us try to create a buffer on this. And okay, what is the EPSG 32640? Yeah, okay, fine. So go to vector, this thing, geoprocessing tool, and buffer. Now I want a buffer zone around Indore district, and that distance I want to keep, say 2 kilometers. 2 kilometers. Okay. Now say run. Close. Now see, if I take it down, you will see. Now a buffer zone has been created. So because it is a polygon, so if you want to know only this much area, what can you do? Can anybody answer this? So I got a buffer polygon. Oh, just a minute. Buffer polygon, which is a 2 kilometer zone around Indore district, and a polygon of Indore district, but not the internal area. So what should we do?
Difference, subtract or difference.
Yes. Difference you have to
So
apply.
from the
Then
buffered
so let
to
us
the previous one.
yes. So this buffered is this one. Okay, so we'll go for geoprocessing and we'll go for difference. Now only the thing is that you have to see the order of difference, in what order you will do. So let us try. It is, yeah, from, okay, let us try this, the problem. Indore and buffered, which one buffered? Yeah, this one. And so on. Yes. So it has written the internal thing. If I just do the reverse, it will give me geoprocessing and buffer, oh, sorry, not buffer, geoprocessing and difference. So I will use the buffered layer here, this one, which is what, it is very difficult. Okay, I will rename it buffer 2 kilometer. Okay, now go to difference, and I will use buffer 2 kilometer, and then here I will use Indore and say run, close. Now see what has happened. So that area has been written. So it is something wonderful. So in your civil engineering applications or even planning or architecture applications, many times you are interested in computing the areas which are lying outside, inside, or something like that. then you can utilize these options in various combinations and can always use it. So I think this is the time to do some hands-on at your end. So I think the data for this particular thing uh, must be with you. So do you have indoor data for map composition? So in that case, I will if you don't have it, I will request Gokhale madam to just share this data. So I'm just sharing this particular
Sir,
thing
I
with
have
her.
shared the data that you sent today morning.
No. This is another one. I think this I shared with Aradhna madam, and I don't know whether you have this folder with you or not. So if you don't have it, I will just right now I will just send it to you so that you can send it to the participants, and on that they can just work. Okay, just a moment. I'm sending you. Yes, I have sent it.
Yes, I have shared the data. I think the participants must be
Indoor data
having.
for map composition. Yeah. So friends, you can just download it and unzip it and just try hands-on, because you've got all the things. Point is there, line is there, polygon is there, and some simple data which I use for that PowerPoint presentation. That is also there. So even you can do some experimentation with that also. So it is 11:12. I think we'll meet after some 10-15 minutes. Meanwhile, you do it, and whatever the problems you are having, as usual, you write it in the chat box, and we'll just see. Okay. So have you received the data?
Yes, sir. Yes.
That another one, no? Not this overlay example, that indoor data.
Yes, sir. We got it now, sir.
Okay, okay. So those who could do something, at least the things which are demonstrated, please update me in the chat box so that we can just proceed further. Hello everyone. If you are facing some problem, then please let me know. Because so far only Nimaji has updated that he has done some hands-on, but others I think they are not responding. So if they are having some problem, then it's better you just open your mic and speak or just write in the chat box. What about Umang Agarwal? Okay. For creating buffer, you have to be careful because you have to change the projection of the layer. Because if it is at WGS 84, then the distances will be required in degrees. So converting 250 kilometer in degree, if you can compute that particular thing, then you can enter the degrees also. But that is not a good idea. So whenever we want to do the distance and area calculation, it is better to be done on UTM projection. So for that, you have to export that file into, you have to save this file as another file, and while saving it, you should specify its um, its projection system to UTM. So you will go here, and here when you save the file, you have to decide a projection EPSG 32643. That is WGS 84 / UTM zone 43N. And how to get it? You can just click on this select CRS, and here you can write UTM 43N and just say enter. Oh, sorry. Then you just type in UTM 43N or something like that. It will just come here, and then you can select it and can use it. Because on my computer, I already used it. That is why it is populated in the drop-down boxes. On your computer, it may not be coming. So you can go to this coordinate reference system selector, and here you can write UTM 43. You'll write something like that. It will appear here in the next box, and from there you can select it, and you can see it is showing on the world map also that UTM zone, that red colored polygon is coming. Okay, this way you can do it. Okay, Madhuri Mittal has also done, but I think this much time should not take. I think it's very simple operation because you have to simply select the two layers and click on that. It will immediately do it. So why you are taking a lot of time? I don't understand it. So that's why I'm asking that if you have some problem, you just ask me. Okay, Umang Agrawal has also done. Good. So shall we proceed further? Because one more lecture is there. Um,
Yes, sir.
okay. So I have given you a fairly good idea what is spatial analysis and how to perform it using QGIS and the data on which I performed it. I've also given you the data. So, and many of you have already tried and done it. And those who could not do it, they have the data with them. They can always try it later on. So now quickly in 5-10 minutes, I will share one problem with you that how we can solve the real life problems using spatial analysis or GIS. So, okay, this is a problem statement here, just 2 slides. uh, Suppose you got a data of wind data is there with you, one shapefile is there, which is having certain polygons, and those polygons having the information about the velocity of wind in different areas. Okay, and you have got a city file that is the location of the city with the population, and you have got a road layer, a line layer, which is the highway. So you got certain polygons uh, having the different wind classes, cities with different population, and highway. 3 layers are there. Okay, and now you have been asked to select the site for the wind farm. You know the wind farms nowadays on the highways, along the highways, you see the wind farm. How that wind farm is, the site for that wind farm is selected. It is not just on the random basis. Again, it is not only the velocity of the wind. There are certain other criteria also applied. Only after that it is selected. So in an area where, so wind class, so we'll erect the wind farm only in the areas where wind power class is 2 or above. So our wind power class file will have an attribute named wind power class in which there will be values like 1, 2, 3, 4, 5, 8, 7. So we'll select only those which are above 2 or above. Okay. And then another condition is that it should be within 5 kilometers from the highway. So whatever area you select, that should be within 5 kilometers from highway. And then it should be within 4 kilometers of the city. And that too from a city where the density of population is 8 and above. So to solve this problem, you can apply the intersection, buffering, these kind of things you can apply and solve it. So just have a look at the data so that I'm not going to solve the entire thing in front of you because it will take a lot of time. So I think, yeah, it's here, wind farm. So I'll quickly show you what is the input and what is the output. The process, we will not do it here because okay, so we have got these 3 layers with us. One is the wind data. Right click on it, see the attribute table. It has got wind power class. So we are interested in 2 and above. So we'll discard this one. How can we discard it? We can apply a filter on this data and we can select where the WPC is greater than or equal to 2. So only those polygons will be visible. We will save it and use it. Then it is saying highways, the areas should be within 5 kilometers from the highway. So we can create a 5 kilometer buffer around the highway. And then cities, it is saying that it should be population density more than 8. So we'll filter out the cities and we'll keep only those cities where this PD means the population density is greater than 8. And then we can perform the intersection of the wind power class with the road buffer. So we'll get the areas which are within the 5 kilometers of the buffer. And whatever area we get, if we clip it again with the cities, again, because it should be within 4 kilometers from the city. So around the cities, we have to create the buffer. Okay, let me see. whether this thing is there or not. If it is already created, I think it will be easy for you to just see it and visualize it. Oh yeah, city buffer is there. Okay, so I'll just go to the city buffer is there, and highway buffer, sorry, city buffer is there, highway buffer is there, and say open, add, and close. Now, so now I have created a buffer on the cities. These are the cities, and similarly we have created the buffer on the highways. So if you intersect this city buffer with the highway buffer, you will get the desired areas. And whenever you do this buffering and intersection process, ultimately you will get the final areas. I think will acceptable. Yeah, final area dot shp. Okay, add and close. Now, if you perform this entire analysis, then ultimately you may have something. So this entire area has been reduced. So you can just go on filtering the things, intersecting them, creating buffers and all that. And you can, so out of this very big area, now whatever area you pick up, these orange colored areas, they are within the 5 kilometers from the highway. They are within a distance of 4 kilometers from the city, and the cities are again having a population density 8 or above. So this is how the GIS can help, or special analysis can help in solving the problems or making the decisions. Okay. So I end this particular part here itself, uh, and we can just have 5 minutes break, and we can just then talk about the next part of it. So 5 minutes is about just whosoever is. I think it is 11:51. So I think we'll start the next lecture at 12. So in 5-10 minutes, you can again just you can complete your remaining work, and those who have done it, they can just take a break. So see you at 12 after
Okay.
5-6 minutes.
Okay.
So anybody wants to discuss something related to hands-on exercise of spatial analysis?
Excuse me, sir. Sir, actually,
Yes.
I have doubts on why we need to change the coordinate system. Actually, we had
See,
that. Now we changed into some other this one also.
actually, this. So you can just try it. Okay. I'll just share my screen once again.
Yes.
Okay. And I go here. And suppose I just take a road. Okay. And I try to create a buffer on this road. So I go to this geoprocessing tool and buffer and say it is asking the distance in degrees. No?
Okay.
How can you give the distance in degrees? Suppose I give 10 degree, it will be too big. Even 1 degree will be very big. Okay.
Okay.
So suppose I get 0.25 degrees. Then say run. It will make it. See what it has done.
Oh, okay.
Okay. This is our
Yes.
road. So,
Okay.
so actually, of course, you can compute appropriate degree equivalent to the distance or meters or kilometers you need. But actually, that latitude, longitude, or the geographic coordinate we used on a curved surface.
Okay.
So the calculation of the distance will vary from latitude to as you move from equator to the north pole or south pole. The the
Okay,
the
sir.
formula of calculation will vary. That is why we have got the UTM projection maps. In that you divide the entire globe into certain rectangular zones, and you
Okay.
set the origin at the left bottom of that rectangular zone. And
Okay.
with reference to that, you calculate the coordinates within that area. So you assume that that particular part of Earth is flat. So whatever you calculate, you don't have to do any trigonometrical this thing. Complex trigonometry is not, because curvature of Earth is not being taken into consideration there. Okay.
Okay.
So that is why for calculation purpose, it is better to go to a proper appropriate UTM zone to which your area is belonging. Okay.
Oh,
And then you
okay.
do it there. Okay.
Okay. Okay, sir. So for this alone, we can use it, right? For buffering alone.
Yeah, buffering, or if you want to have the area. Say, for example, okay, one more interesting thing I will show you as you asked.
Yes, sir.
Suppose I'm interested in finding the area of these tessile polygons. So I'll just remove this buffer and all that. So this is the tessile polygon, and okay, even the roads I will just put off. So you see the attribute table. There is only 2 columns,
Yes, sir.
but I may be interested in knowing the area of each polygon. So there are tools like this: measurement line, measure area. But what they will do? You have to draw something here to do this, no? And if you want to have the area, you have to draw the entire polygon.
Okay.
And suppose you got some thousands of polygons, then it will be a tedious task because the data is already stored in the vector format. So system should be able to calculate it for you in just one go. Okay, so we can have there is an option called research tool, analysis tool, and in that actually there are so many options. So many times you forget what is where. Okay, geometry tools. Yeah, it is in geometry tools, and there is a add geometry attributes. Geometry attributes are what? Area and
Yes, sir.
perimeter. Okay, so you just click on it and select the tehsil and compute from layer CRS. The option is there and say run. Close. Now, one more layer has been created, memory layer has been created, and you see the attribute table. You will find the area and the perimeter here.
Oh,
Okay.
sure. Yes, sir.
So if it is in WGS 84, it will come in degrees,
Oh,
degree
okay.
minutes. And okay.
Okay.
So yeah, probably this layer is not in that particular coordinate. And even the new versions of QGIS are, yeah, it is in 32643. Okay. 32643 means it is UTM projection.
Okay,
That is
okay.
why the area is coming in square meters.
Square feet.
Otherwise, it will come in square degrees,
Okay,
and that will be meaningless for us. Okay?
okay, okay, okay. It's more clear, sir. Thank you so much.
Okay.
Sir, Abha Gupta madam has also raised her hand.
Yes, 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 please. Yeah, madam.
Do you have any query, Abha madam? I think she is not there. So you can continue.
Okay. So I think we proceed to the next topic. So now we have seen in this presentation that how we can import the point data through a CSV file and how can perform the basic operations like on the geospatial operations or the special analysis operations like buffering, clipping, intersection. And I also demonstrated that how these can be used to solve some real life problem. Okay. So now we move to the next part. That is the just a minute. I'm having a phone call. Yeah. Sorry. Sorry for the interruption. Basically, so far we have seen that how to create the data, how to modify the data, how to query the data, how to perform the spatial analysis on data. Now, there may be some different data sets are available. So now we have learned how to input a map from the topographical map, Survey of India map, and how to even open a satellite imagery in QGIS and digitize it. Of course, for that you should know the image interpretation. Only then you will be able to trace the features. But if you know it, you can comfortably and very conveniently do it in QGIS. And if you've got an old map, you can scan it and can do the digitization. If you've got a GPS, you can bring in the coordinates, store them in a GPX file or in a CSV file and can import it into the things. But nowadays, few more data sets are available. They are becoming very popular, and that is basically the elevation data, the topographic data. And civil engineers, many of you are from civil engineering background, so you are always in need of the topographic data. And I should say that, of course, the data which is available through the various platforms, that may not be of as high resolution as it is needed by you people, because when you construct a road or canal, probably you need the data to be in the accuracy of centimeters. But the data, topographic data, which is available on various platforms, that is of few meters resolution, say 5 meters, 10 meters, 20 meters, 30 meters, something like that. So that may not be quite suitable for your civil works, but overall regional modeling, regional planning, for that it can definitely work. So that is a wonderful area which is opening up, and through the remote sensing techniques, we can collect the elevation data and we can utilize, and very seamlessly we can integrate it in our GIS software. And from that we can perform various kind of calculations, and even we can see the terrain in 3D. So many times the visualization is a very important process, because we want to see the things, because seeing a contour plan may not be easy for everyone, particularly those who don't have a background in civil engineering or geography or geology. For them, realizing what the contour map is showing may be a difficult task. So for those, or even for the students also, we can create the 3D of the terrain using the GIS techniques and using the topographic data. So the very popularly available topographic models or data, that is known as the digital elevation models. And you might have seen it and you might have used it also, but many of you, it may be a new thing for many of you. So now we talk about the digital elevation model. So digital elevation model, just a minute. Okay. So elevation means it is related to the topography or the height of the terrain. Okay. So digital elevation model, in short, it is known as DEM. A digital elevation model is a representation of the bare ground topographic surface of the earth, excluding trees, buildings, and any other surface objects. See what we do as a civil engineers, you know the contours. You prepare contours, and when we prepare contour, what we do, we just use auto level or total station or whatever the technique we use. We try to find the elevation of the certain points on the surface of the earth. We are not interested in the buildings and all that. Of course, if you want to add the building, there are techniques to add that data to the contour plan or the 3D model or whatever it is. But basically, we are interested in the details of the surface, that how the surface is varying. So using that surface, we can just compute the volumes, we can compute the cut areas, the cut volumes, fill volumes, and if you add something to that, how that the final level will be there, how it will appear. So for that, we perform the various kind of topographic surveys. And you know the topographic survey is a tedious task, it's a time-taking task. But of course, civil engineers are forced to do that because they want a high-resolution data. But nowadays, some modern techniques are coming, so that can save a lot of our time, and it not only saves the time, it can create the high resolution data also, even for the civil engineers. So digital elevation models are types of raster GIS there. Say we talked about the vector data and raster data. Vector data, you know, your shape file is a vector file, because if you are storing points, so what you are storing the x and y coordinate, latitude and longitude of that point. But if you want to store a map, if you scan it, each and every pixel from left top corner of that map to the right bottom corner of that map is scanned and stored. So it is not storing the coordinates, it is storing the pixel values. That pixel value may represent reflectance of the ground, or some kind of information. Even it may be a topography, it may be the information of the elevation. So like you have got a in which you have got the reflectance of the each pixel on the ground. In a digital elevation model, instead of the amount of light which is being reflected from that area, we will have the height of that area. So like that, you can have a grid, and each center or each grid is having information about the height of that particular grid area. Okay, and using this information, we can just visualize the terrain in 3D. Okay. Now in DM, each cell of a raster GIS layer has a value corresponding to its elevation. So because it is a rectangle image, if you tell the left top coordinates, the XY at the left top corner and the XY at the right bottom corner, you can always compute the X and Y of any pixel in that map. It is just like a graph, and the value which is there on the pixel is the elevation. So that raster will hold the X, Y, and Z information of each and every pixel in that map. Okay, and the details of the ground surface, that is pixel values, will be better modeled with a smaller grid spacing. So it is very, so when you perform civil survey, uh, you decide grid, and on that grid you compute the heights of the points. Okay, so if you want to represent the ground, reduce the space construction, I think you keep a very less distance between your observation points. But if you are doing a survey for some pond or some reservoir area, you just keep the distances larger because you're not interested in the minor details of the ground. So similarly, the better the DEM, the smaller will be the grid. So the larger will be the digital elevation model. It is exactly like we have a high resolution photograph. Size of the high resolution image will be large, and the same area, if you store or scan with a camera which is of lower resolution, then the same area details, not much details will be seen, and the size of the image will be smaller in terms of pixels, as well as in terms of memory also. So digital elevation is just an image holding the information of elevation. Okay. Now, how to generate it? How they are created? Say there are various ways of doing it. Say we can create it from manual data collection also. So whatever the ground control point GCP you pick up from auto level or something, using that also we can create. Because ultimately what you do when you pick up the points from the ground using auto level, you contour it. Okay. And in contouring, what we do the interpolation. But if your grid spacing is better, then you get a better contour. If your grids are I mean the AutoCAD data collection points are random, then you may not have a very good representation of the terrain. Okay, so you can have the ground data collected yourself, and from that you can calculate the contour. From that contour, you can calculate a triangular irregular network, which is again a vector kind of data. You divide the surface into smaller triangles, and depending on the slope, the orientation of the triangle will change. So your surface will appear in a surface which is having the triangles of different orientations. Okay, and even from that triangle, we can compute a surface where you can just move from the one corner to the another corner of the map or scene, and can compute the elevation like you do in contours. Because you've got two contours with me, one is of 100 value, another is say 80 meters or 90 meters. I can always compute the elevation of any point between these two contours. So similar way, from a tin model, I can compute a surface where the interpolated values of the elevations will be there, and I can create a raster file out of that, and that will be a digital elevation model. But in practice, what is happening? We don't generally create it from our ground data. They are created by automated systems. They are created from aerial photographs. They are created from satellite data. So we may have this photographs, use the zero pair of satellite images, and from that, using some ground control points, the digital elevation models are computed. You might have heard of ISRO Google. ISRO is a geo portal, is a portal for geoinformation from ISRO, and anybody can just access that portal and can download the satellite image, digital elevation model, and so many more other things. The thing is that you have to register to that portal, and registration is of course free. So you can use your email ID to register on that portal, and it is the data which is available there. And some of the data is available for download also, including the digital elevation model. Okay, so that has been prepared by using Cartosat satellite. So using that satellite, they are creating the digital elevation model. You can download it and you can perform the various kind of computations from that. Okay, and then another way is that you can use a radar. So there is a shuttle radar topographic mission. USGS, United States Geological Survey, or NASA. NASA actually is behind us, and they are also having the global data of the elevation. So that is the SRTM data. If you Google SRTM, you will find the website of the related website you will get, and from there you can download the digital elevation model computed from radar data for any part of the globe. Of course, the resolution is not very high, but for geomorphology and other applications, it is quite good. And then the latest thing is going on is the LiDAR, light detection and ranging. Like you send a radio wave and it is reflected, and on that basis you compute the distance or the height. So you can precisely use a laser ray and a laser to compute the distances. So it can give you a very high resolution data. A very smaller feature can be picked up. So the minor variations in the heights can be very well detected using the LiDAR. And LiDAR can be used in a on an aerial platform. You can put it on a drone or an aircraft, or even you can mount it on a vehicle and can collect the data from itself. So you can put a LiDAR antenna like this, look into the road, and you can just drive on that particular road. So whatever is the profile of the road or the terrain, that will be picked up, and you will be able to have a 3D representation of that. So this is the way using which we can have a pretty high resolution data collection of the data collection using these modern techniques. So whatever the data is ultimately collected is it may be in the form of a digital elevation model. Okay. Now this is just a photograph of a digital elevation model. When you just download a digital elevation model, it will be a grayscaled thing. Means the elevation which is at higher level may be either white or black, and anything in between will be in gray colors. But using the computer software, we can perform a special processing on it, and we can assign the colors so that it becomes visually appealing, and it conveys the topography and slope and everything in a much better way. So as you can see, this is digital elevation model of the Mount Everest region. You can see probably this is the Mount Everest, and there is a scale is also given here. The darker the color, the higher the elevation, and even with the elevation, the color is also changing gradually. So now the low-lying areas and other things you can very well see it. Even the glacial valleys and all those things. These are all the glacial valleys you can see very well. So anyway, this is so it is just not for viewing purpose. So viewing is one part. Okay, but there are other applications. We'll come to that. So one word is digital elevation model, another is digital terrain model, another is digital surface model, DEM, DTM, and DSM. So DTM is basically mostly considered synonymous with the digital elevation model, but in the US there are slight differences between DTM and DSM. So we will not go into detail of that. So right for the moment we can consider that digital elevation model and digital terrain model is the same, because they are representing the height of the surface of the earth, ground surface they are representing, their elevation they are representing. Okay. Now another is digital surface model. So surface model means represent the mean sea level elevation of the reflective surface of the. Say if you are seeing from the top, you will not always see the ground. You will see the buildings, you will see tree canopy. So when you have a radar data collection or something like that, you will have the like you're seeing in this particular photograph. You are seeing the buildings, and then the tree canopies are available. So this, whatever the top surface has been generated, that is the surface, digital surface model. So DTM will be below this. DSM will be, so DEM plus the man-made features and forests and trees and this thing, that will make the DSM. Okay. Here also you can see it. Say this is the topographic surface shown in green colored line. If your data is having this green colored line information, that is the only the information on the ground. It will be DEM. And if your data is having the trees and canopy of the trees and buildings and other things, then it will be DSM. From DSM, we can compute DEM. Only the thing is that we have to process it in such a way that the features which are above the ground, they are eliminated. That elimination is not very simple. But in LiDAR, there are processing tools available using which you can eliminate the surface features, and you can have the details of the ground. Okay. Now, how can we get the digital elevation models? As I told you, DEM data we can get from Bhuvan Indian Geoportal from ISRO. So anybody can log into this Bhuvan portal and can download even the satellite data of different dates, and even the digital elevation model of Carto DEM is available. You can just download it. Then I talked about the Space Shuttle Radar Topography Mission, SRTM. So SRTM can also be, downloaded. Data can be downloaded. Then nowadays, even Esther Global Digital Elevation Model is coming, and this is again from NASA, Propulsion Laboratory. This is also a very good quality data. And there is one more, JAXA, Global Allows 3D World. This is a Japanese agency, and they are also providing the data for the digital elevation for the entire globe. Now, here's a link for that. I think we should see it. Just a minute. I don't know how it will. Just a moment. Yeah. Now I can click on this. So that particular website will be opened and you will be able to see. So this is the globe, and there are different versions of data is available here. I think it is not there. Okay. Yeah, that's it. So we move to the Indian part. We zoom it.
संजय सोनी से बड़ा नहीं है, तो कोई है नहीं।
ये अपना माइक्रोफोन ऑफ कर दें जी, अनिल सिंघाई. Okay, so now you can start seeing the Himalayan mountains here, the Indo-Gangetic alluvium, Thar desert, and rest of the peninsular part where you got the Western Ghats and all those, that they start appearing as you zoom in. Now you zoom in further. These are the Aravalli mountains, you can see beautifully here. These are the part of the Malwa Plateau. This, the Narda Valley. I mean, these are the Vindhyan ranges, and these are the Satpura ranges. And in between, you have got Narda Valley here. Just zoom in further little.
Sir,
Even you
what
can
is
see the
the data
Narla Valley.
resolution?
I think it is 10 meters. And this one is 10 meters. But if you want to purchase the data, then they can provide the data of even higher resolution also. But you have to pay some price, heavy price for that. And this is free data. It can any part of this can be downloaded, but resolution is probably 10 meters here.
Okay.
So you can see the Narda Valley, beautiful depiction of Narda Valley here. And even I can show you this part. This is Indore. Indore city is situated somewhere here, and these are the hillocks which are seen near Indore. Above this, it will not zoom. So this is the maximum zoom level. But even at this zoom level, I can see the when you download it, then you can see the things slightly in a larger format, larger size. So beautifully, you can see the topography and everything here. And if I just go to some part of Western Ghat, so this tool is really good for teaching the topography because seeing the things from contour is really a challenging thing for a novice. You see, it is beautifully depicting the topography. But this is the maximum zoom level. Above this, it will not go.
Sir, can we see one downloaded part that you just suggested?
Yeah. I will show. I will show how to open it in QGIS. That also I will show. Okay. Now see the some part of Himalaya. So this data is amazing. This is the best one available. Even the alluvial cones and fans, the rivers which are coming, dropping down from the Himalayan mountains, even those you can beautifully see. So for the people who study geomorphology and who just want to have some kind of representation of the terrain, for them it is really good. And you can definitely take some decisions based on this because it is accurate. But I know the civil engineers cannot deal with the 10 meters data. For them, it is a too coarse resolution. Anyway, so this is it. Okay, got this. And another is the light detection and ranging. So LiDAR data for India, it is not available. But there are certain private agencies, they conduct the LiDAR survey on demand. And nowadays, I told you that for this road construction, even they are asking for DPR, they are asking for the LiDAR survey. They are not now no more relying on this dumpy level or total station data because LiDAR is more accurate. It beautifully pick up the details of the ground. So suppose you are having a case of a road widening, you can just mount a lidar in one vehicle and move on the road and can collect the data from the sites. So whatever is the topography there, the depressions, elevations, whatever is there, it is very well picked up, and then you can just prepare the cross sections and everything from there. The way you do it with your original survey data, you can just extract the points from there and can just have your cut fill calculation design. So this is another positive thing. And we are not only monitoring the surface through this remotely like Mars data is also being collected using the LiDAR. So Mars orbiter laser altimeter. Altimeter is an equipment which is used to measure height. Okay. So it is a kind of a remote altimeter because you don't have to go to that terrain. You can operate from somewhere else and can collect the data. Okay. So MOLA is also there. These are some of the photographs of the MOLA dam showing two hemispheres of the Mars, the two different sides of Mars. You can see the volcanoes and the topography, and it's really amazing. Amazing. It's a beautiful depiction. So how many details are being picked up, you can see here. This is another LiDAR DEM. You can see very well have a good representation or of the topography here. So it's Hawaii volcanic archipelago, and even so it is just a raster file, means each grid is having the information of elevation. Then you might be wondering that how we are having a topographic surface, because raster will be a 2D thing. Okay, you cannot raise it like this. But because the information of elevation is available, so from this we can compute a hill shade model. Suppose there is a topography like this and the light source is here. So this part will be illuminated, the other part will have the shade. And depending on the sun angle and the height, the shaded areas will vary, the intensity of shades will vary, the brightness of the slopes and the surfaces will vary, because how they are oriented with the reference to light direction, it will depend on that. So those kind of computations can be done, and a surface can be rendered using that. So this is that kind of a surface that has been rendered using some kind of a hill shading, hill viewing techniques. Okay. Here also you can see even all the same area, but some part has been collected at even a much higher resolution. So you can see the cracks and in the rocks and all that, and even the depressions, everything you can see very beautifully. So if you compute something like, if you want to have the elevation of some particular part, or you want to have a cross section of it, or in a profile and along any direction, you can always compute from this. Okay, because each pixel is having the information of elevation. How it is appearing like this? Because some specialized computerized techniques have been used to display this data in such a way that it is representing almost a real ground view. Of course, it is not a real ground view. It is not a photograph. It is the data of the height, which is being depicted in such a way that if you are seeing the things from, the light is coming from the left top direction, then how the shadows and the illuminated areas will be formed. Why I'm saying that the light is coming from the left top, the light is coming from this direction, because you can see the shadow here, and this particular face, it is a vertical face, I can very well see, and it is very brightly lit. This is brightly lit. This is because the slope is gentler here, so it is less darker. The slope is steeper here, it is more darker. So this human perception we already have, this built-in capacity we have within us. So we don't have to apply some specialized techniques to read this or to interpret this. But if you have got a computer which is programmed to interpret or extract the information from this data, we can compute the surface, we can compute the volume which was available here, or you can just fill this. If you want to fill this particular terrain, how much volume will be needed? All those kind of things can be computed from here. Okay. You see, as a civil engineer, you are more expert than me about these particular things. Okay. So now we'll talk about some basic techniques. Suppose you got a. So I told you that near Indore you got certain hills like this. This is one hill. This is second hill. Third, fourth, five. And I showed you this and told you that you can see the hills in Indore. It will be very interesting to see. You see this part. Although it's very small. 1, 2, 3, 4, 5. And if you see, where it is. You see, that's the same hillocks here. Same thing. Anyway, so this is a contour map. And if I want to represent this contour map in 3D, I want to compute a surface or a digital elevation model out of this. I can do it. For that, what I have to do? I have to digitize the contours in QGIS. And once I digitize, the contours will appear somewhat like this. And when I digitize them, I have to enter the Z values as a field value or within the data itself. In the data, I can just enter the X, Y, and Z coordinate of each and every point. Z coordinate I have to manually enter. That cannot be picked up by digitization. Because when you move the cursor in digitize, the X and Y values are picked up, but Z value cannot be picked up automatically. That can only be picked up through a radar or a lidar or something like that. Okay. So that is a different technique. That's why those things have been devised. So we can pick up the contours. Then from contour, we can compute a surface kind of a digital elevation model kind of a thing, where depending on the values of the contours, we just have the shades. Darker the shade, higher is the elevation. Lighter the shade, lower is the elevation. So that thing has been computed. Now from this, even we can compute, or from even this contour map, we can compute a tin model, triangulated irregular network. You see, small triangles are there, and these triangles are based on the distance of the data points. Okay, if the smaller the data points are closely spaced, then you will have the smaller triangles, and you will have a better depiction of the topography. If the data points are sparse or are away from each other, you will have a larger triangle, and you will not have a very smooth representation of the topography. So as you can see here, there are no contours in between these areas. So very big triangles have been formed. Here the contours are quite close to each other. So that is why we are having very good representation of the hillocks here. But the rest of the part is not being shown in a very smooth way. So using GIS software, from contours, we can compute a tin model, and tin is a way of representing the digital the elevation information in a vector format. So each node of this triangle is having the information of X, Y, and Z. So like this entire surface is made up of the triangles of different orientation. This orientation is computed based on the slope of the ground, and the slope can be computed from the contours. Okay, so complex trigonometry and all that. But softwares are that's why we need the software, because manually if you try to calculate it, it will be a very tedious task. But software will calculate it within minutes and will give you a representation of the terrain like this. Okay, then from this vector we can generate a smoother digital surface, digital elevation like this. So our 3D surface has been created, in which you can see the hills here, and you can even see the drainages and everything. It's beautiful. And even another benefit is that you can rotate it the way you want. Of course, this particular drawing in this slide cannot be rotated because it is just a screenshot. But when you create it, you can rotate it the way you want. You can see it from the top, side. The viewing position can be changed. The altitude, everything can be changed. Then there are certain other applications of it, that we can have a view of the ground, and using this we can even perform the different kind of calculations. So you can see this is the area here near to the hill. Some plain ground is there, and suppose this plain ground has to be filled up to certain level, then how it will look like. Before filling, you can compute, because the basic data is available with you. Now you can just manipulate the pixels or the values in this area, and can increase the elevation. So once you increase the elevation, the surface will reappear, will look quite differently. So how a thing will be seen after a cut, how the thing will be seen after a fill, you can just visualize well before filling it or before cutting it. Or you want to modify a surface in certain way, you can just have that surface, you can have a computation, a digital model of that surface, and you can integrate it with the original digital elevation model and before the construction. The same thing. This data was created by me long back. Okay, so this is not something taken from internet or something. Okay, so although I'm a geologist, close contacts with the civil engineers. So this work I did for some of my friends. So initially they are having some AutoCAD drawing, elevation data was there, so it was converted into this 3D, and then they had another layer that this area they will fill up to this limit. Now, how it will look like? So this will look like this after filling. Then this is another thing in which some company was being some factory was being created on a hill, and they just wanted to see that how that slope of the road and other things will look. So there was just a contour plan and AutoCAD drawing was there. Then from that contour plan, because in AutoCAD drawing, the different levels were specified that they will create a platform of this particular elevation, of this particular size, then they will cut another platform of this height at this size. The road will be like this. So everything was coming from some kind of a drawing, and then using some kind of software tools, this kind of a scene was created. Then from the drawing itself, the buildings or the structures which they wanted to make, they have been created. So ultimately, we got a 3D, and we could see it from anywhere, any angle. That is it. So we can compute the things from a field data. Yeah, this was done long back. Says I think probably some 12 to 13 years back. That time, this digital elevation data, all these things were not available. But this is something different because a hill was existing, the contours were there. Now here we are trying to cut the hill and want to see before cutting how it is appearing. So this is the data processing, and this is what GIS and different. Of course, your AutoCAD can also do it. So this is what the digital elevation model data can play a role in doing the things. This is another example of a geological map which we give to the BSc students. And because you are civil engineers, you know that in this I'm having geological contacts here, and these dotted lines are the contours. So these contours are like this. So there's a hill here, and so it is somewhat a terrain like this, flat, and the slopes are like this. But when we tell the student that there's a hill like this, it is very difficult for them to realize that how the topography is appearing, how the slopes are varying. There's a small valley over here. They don't realize it. They don't understand. It's difficult. So we thought, why not to create a 3D out of it? So we just trace the contours from this map, and then again a tin was created, and then the surface was created, and then we ultimately had a 3D. And this 3D was oh, sorry, it's not, what's the problem? Just a minute. Mhm. Just a moment. I will show you. Yeah. Oh, that link is not there. Probably no. You can see it now here. So now it is very easy to realize it what exactly it is. So viewing is one part which is really very important, and then modifying the terrain and doing the things, and then again revisualizing it, that is another part. And then whatever modifications you are doing, what kind of cost will be involved, because modification will need either cutting or filling. So that is very well can be shown, as well as it can be computed using this kind of data. So just by integrating the viewing and the calculation, we can bring out the amazing results, and stunning results can be brought and can be seen. So this is how this geological map will look in 3D. So what we did, we just wrapped that scanned map again on top of that surface which we created. This is it basically. So we just show it to the students in the class after giving them this paper map. We explain these are the contours, they look like this, and then we show this animation so that it becomes clear to them. There's one more thing is there. This is a contour plan, and some kind of tunnels are there at some level beneath this ground. And then from this, we have computed this tin model. Tin we have created, and from tin we have created a surface, and we are trying to visualize this surface in 3D. You can see animation here. So visualizing this from a 3D from a contour map is difficult, but now it is giving us a very good picture that at what depth that particular structure is lying, maybe a pipeline or something, and how the topography is there, at what depth the things are there. This all we can very well see it here. This was also done long back, and at that time the QGIS was not powerful. So this particular thing, the animation you are seeing, it was done using ArcGIS. In ArcGIS, we have got one module called ArcScene. So using ArcScene, this thing, and the geological map which we use to show in the classroom, and we have got more such maps with us. There is not only the one map. So we put in some effort and created these kind of things for the demonstration, and it was done in ArcGIS. Now QGIS 3 onwards, there is an option for creating the 3D. You can create a 3D data, you can visualize it in 3D, you can rotate it the way you want, but this facility is excellent in ArcGIS. It is not so good in QGIS. But the things are improving gradually, and we hope that in future also we may get some enhancement in that, and we can get a better option. Okay, so now we come to the applications of digital elevation model. So as you could very well imagine that what may be the applications, because for a geomorphologist, we want to see the topography in 3D. So then he can describe that particular landform in a much better way. He can not only see and describe, he can perform the different kind of measurements. He can compute the slopes and all those kind of things, and depending on that, he can perform various calculations. He can derive different type of conclusions based on that. Okay, so that is a wonderful thing. Modeling of water flow and hydrology, because slopes are there, we can derive the drainages, we can delineate the river basin or the catchment area. That is automatically it is possible. Modeling soil or erosion or mass movement, that all these modeling processes, they are related with the slope. So that can help in doing that. Relief map can be created, because 3D generation, you have seen good number of examples of the 3D relief map. Rendering of 3D visualization means you can rotate the things. You are not only creating a relief map, you are interactively, you are in a position to rotate it and view it the way you want. Then it is also used for the rectification of remotely sensed data. Suppose you got a digital elevation model, correctly created model is available with you. Now that data can be used to correct the remotely sensed data, because when we take the satellite images or aerial photographs, they have got some inherent problems because of the motion of the aircraft, because of the tilt of the aircraft and the curvature of the earth. So that data has to be corrected. And for correction, we need the ground control points, the X, Y, and Z value of those ground control points need to be fixed very precisely. And using that, we can modify this. So this kind of information is already available with some satellite launching agency. They can utilize it and can do the things. Climatology, because the sunlight orientation of the surfaces, so many things we can do. Urban planning, of course, I think I am not the right person to comment about it. Logistic and communication. The telecommunication company, because mobile companies erect the towers on the buildings. So the condition is that the top of these two towers should be in a straight line. They should be visible to each other. So they need to know the topography. Basically they need the digital surface model of the city, so that they know how big trees are there, how big buildings are there. So on that basis they decide and erect their towers and then design it. Okay, so that the signal travels smoothly within the city. In mining also, we have got great applications because for mining, particularly on the underground bodies, we have to visualize the shape and size of the body. Once we have an interactive view of the shape and size of the body, we can plan a correct mining method for that. Even if we want to plan an open pit mining, then how the open pit will be started after 5 years time, how it will look like, how much volume will be excavated. And if you extract that particular part and heap it up in the or dump it in the surrounding areas, how the topography of that will be modified. All those things can be very well visualized and precisely calculated using these sort of tools and techniques. So thank you very much. So this is what I just wanted to convey you related to the digital elevation model. Now we can see some data so that you can have a real feel of it. I think I'll close it. Yes, start. Raster data. Okay. Okay, I will just show you first raw raster data. This is the file probably downloaded from Bhuvan. It's saying very layer. Okay. It's XML. Okay, fine. Auxiliary. This is TIFF file. Yeah, this is the one which I should add. See, this is the actually the data. It will be in grayscale, and you can see that the white portions are at higher elevation and the darker portions at the lower elevation. These are the elevations 754 and 167. So it is a part of the Narda Valley. I think the JAXA site is open here. I can tell you from where it is coming exactly. Just a moment, let me locate it. It is this part. Sorry, no. Yeah, this part of the terrain, this particular area. So this is it. And you have got the various options in the properties and symbology. You can tweak around with various options here, and you can convert it to hill shade. Say, for example, I told you about hill shade. Now it is giving me the altitude of the sun or the light source, and the angle elevation I can modify and can say apply and see. Okay, now you see it is appearing like a photograph. And if I want, I can change the things the way I want. Okay. And if I go to the raster option and then go to raster analysis, then there are various things I can do. I can calculate the slope. I can extract even the contours, projection, miscellaneous, sign projection, extraction. Yeah, contours. It will take time if I click on it, but if I click on it, it will just work on it, and whatever the interval you decide, it will work on it, and it will create a new layer that will have the contours of this area. Okay, so that is it. Now we can beautifully process it to show stunning results. So that I will show you. I'm not going to process it in front of you because it will be a time-taking process, and if I If I tell you so many things, you will get confused. So I'm just telling you the pathway. If you are having this kind of data, you can do this with it, and this is the result which will be seen. Okay, start with this. See this. This entire scene, what I showed you was a part of that. Now here, see, beautifully the Narda Valley is coming. This is that Omkareshwar. You might have heard of Omkareshwar temple, Jyotirling. This is Omkareshwar. This is Omkareshwar Dam. Even the dam line can be seen here. So this is, and Indore is here. These are, I was talking about these hills, the contour which you saw. Even you can see the buildings and some roads and something. Smaller hills are there. This is a road going like this. This is probably Agra Bombay Road, AB Road, very famous road. But after this, it will not show. Even some big building is there. This top is appearing here. So this area is the southern slope of Malwa Plateau, and this river system is going and joining Narmada Valley, Narmada River. So it's a tributary of Narmada, and whatever drainage lines you are seeing, they have been computed from this model only. I have not traced them from satellite imagery or from topographical maps. These drainage lines have been extracted from the digital elevation model. You can see very well, see this area. It's very well the drainages are fitting into that. So using the slope and this thing, this QGIS has computed it. One more thing that military people do, they do the view shade analysis. View shade analysis they do. Suppose they are having some army troop here and they want to go to this area and in higher elevation some enemy is sitting. So then they can well in advance they can compute that what are going to be the areas if they will camp there, then they will not be seen from that particular height. So they can have always set the viewing position and then set the direction, and then the topography is there, so they will always find these are the areas where the person sitting on top will not be able to see them, so they can use it for the defense as well as for the attacks and offense also. So not many applications are, even the geological formations, their orientation is very beautifully coming up here in this. And here, this is the part of the Indira Sagar Dam is somewhere here, not beyond this. Okay. This is also a linear ridge. So beautifully, the topography is picked up. And I think we can try if can generate the contours. Input layer is crabbed DM. Okay. And say run. Computer is fast, that's not a problem. So let us see how it will do. You see, you got all the contours here. Even the elevation values are also there. And if you want, you can again style it and then you can categorize them based on this elevation and classify and apply. Okay, so you can have a beautiful contour map. So how ultimately it was made, we created a hillshade first, and then we created a graduated map. And then the transparency of this graduated map was slightly reduced so that the hillshade was available, is visible below this. So if I remove this, it will appear like this. If I just remove this and put this, it will appear like this. So what I have done is we have created a hillshade first. I made a copy of the same layer. On one layer, I made a hillshade. Another layer, I just colored it, pseudo color, and modified the transparency of that layer. Okay, let us see here. Okay, transparency is here. And if I make it and say apply, it will appear like this. So there are different techniques to do it. Okay. See. So I hope the things are making some sense now, and you must be able to understand some utility and fundamentals of this particular new thing. So this is all from my side regarding this. If you got some questions, you are most welcome.
Sir, please share the DM source slide.
I can't hear you properly. Please speak again.
Please share DM source file. There is one slide
I
showing
showed
Aster. So please share it with
Jaxa.
us. Okay.
You can use any. It all depends on the purpose, no? So you can use even Jaxa data. You can use Aster data. You can use. But Jaxa is really good. Jaxa is much better.
So, thank you very much, sir. It was a very wonderful session. I think there is so much to explore, and with time, I think we will all need practice, and with that, we can do much
Yes.
with this software. And I think there is a session of you tomorrow also in the morning. So we will meet tomorrow. If there are
I
some
think
queries,
I wanted to just slightly modify that morning session.
okay,
But anyway, I will talk later in the evening. Okay, no problem.
okay,
Yeah.
sir. So participants, we will now break for lunch, and again at 2 p.m. Please join again for lecture by Dr. Kakoli Saha. So thank you all of you for joining. Thank you very much, Dr. Shailesh Chaure, sir. Thank you.
Okay.